Hello my friends, and welcome back to Sky Creative Channel. Today we're diving deep into some of the most fascinating underwater construction projects and bridge engineering marvels from around the world. So grab your favorite cup of coffee and let's get started. Let's start our journey in the Persian Gulf, where one of the most ambitious underwater construction projects in the Middle East is taking shape. The Khor al-Zubair Immersed Tunnel in Basra, Iraq, represents a masterpiece of modern engineering that will transform transportation in the region. This remarkable immersed tunnel stretches 2.5 kilometers long and features 6 traffic lanes plus a dedicated emergency lane, making it not just the longest tunnel of its kind in the Middle East, but also one of the most sophisticated. Built by South Korea's Daewoo Engineering and Construction, this project is part of the larger Al-Fa Grand Port development, which will establish Iraq as a major maritime hub in the region. Now you might be wondering, what exactly is an immersed tunnel? Well, it's quite different from traditional tunneling methods. Instead of boring through the ground, engineers construct massive concrete segments on land, then carefully lower them into a pre-dredged trench on the seabed. It's like building with enormous Lego blocks, except each block weighs thousands of tons. The construction process begins with creating a precisely engineered casting yard where the tunnel elements are manufactured. Each segment is a marvel of engineering. These aren't just concrete tubes, but sophisticated structures equipped with advanced ventilation systems, lighting, emergency exits, and waterproofing technology that must withstand the immense pressure of the water above. The construction relies on some truly impressive machinery. Massive floating cranes with lifting capacities exceeding 3,000 tons carefully position each tunnel element. These aren't your typical construction cranes. They're specifically designed marine vessels equipped with dynamic positioning systems that can maintain their exact location despite waves, wind, and currents. The immersion process itself is incredibly precise and time-consuming, with each operation taking approximately 16 continuous hours. During this critical phase, the tunnel segment is slowly flooded with water in a controlled manner while being lowered into position. It's like performing surgery on a massive scale, where millimeter precision is essential. One of the most critical aspects of this project is the sealing system. Trelleborg's advanced sealing systems ensure the tunnel remains watertight, using specialized rubber gaskets and compression systems that create permanent watertight connections between tunnel segments. These seals must withstand not just water pressure, but also the thermal expansion and contraction that occurs over decades of operation. Throughout the construction process, quality control is paramount. Every weld, every concrete pour, and every seal installation is monitored and tested multiple times. The project employs advanced, non-destructive testing methods, including ultrasonic inspection and pressure testing, to ensure that every component meets the strictest international standards. This incredible project demonstrates how modern engineering can overcome seemingly impossible challenges, creating vital infrastructure that will serve the community for generations to come. From the Persian Gulf, we now travel to the glamorous Principality of Monaco, where French construction giant Bouygues Travaux Publics has achieved something truly extraordinary. They've literally created new land from the sea. The Monaco Offshore Extension Project is a testament to what's possible when cutting-edge engineering meets environmental consciousness. This offshore urban extension creates 6 hectares of new land, enabling the development of a new eco-district that includes residential space, public facilities, and commercial areas. But this isn't just about creating more space for one of the world's most densely populated countries. It's about doing so in harmony with the marine environment. Imagine trying to build new land in the Mediterranean Sea between 2 marine protected areas, while ensuring zero negative impact on local marine life. That's exactly what Bouygues faced. The maritime infrastructure consists of land reclaimed from the sea, surrounded by a protective belt made of 18 reinforced concrete caissons placed on an underwater rockfill embankment. The caisson precasting area is located in Marseille-Fosse, the large French seaport, where these massive structures are manufactured with incredible precision. Each caisson is a geometric marvel, trapezoid-shaped reinforced concrete structures that are 26 meters tall and weigh an astounding 10,000 tons each. To put that in perspective, that's equivalent to about 50 fully loaded Boeing 747 aircraft. The manufacturing process involves creating highly specialized concrete mixes that can withstand decades of saltwater exposure. The reinforcement steel is positioned with millimeter accuracy, and the concrete is poured using advanced techniques that eliminate air bubbles and ensure uniform strength throughout the massive structure. Moving these massive caissons from Marseille to Monaco is an engineering feat in itself. Specialized heavy lift vessels, essentially floating factories, transport each caisson across 200 kilometers of Mediterranean waters. These vessels are equipped with ballast systems that can precisely control their trim and stability while carrying such enormous loads. The installation process is where the real magic happens. Each caisson must be positioned with incredible accuracy on the prepared seabed. The vessels use advanced GPS positioning systems accurate to within centimeters, combined with sophisticated underwater surveying equipment to ensure perfect placement. These precast units are fitted with absorption chambers, representing a breakthrough in coastal engineering. These chambers are designed to dissipate wave energy, reducing the impact on both the new infrastructure and the existing coastline. It's like building a massive shock absorber for the ocean's energy. Creating this 6-hectare offshore space between two marine-protected areas illustrates the particular care given to respecting the site's biodiversity. The project includes artificial reef structures integrated into the caisson design, creating new habitats for marine life. Advanced monitoring systems track water quality, marine life populations, and sediment movement to ensure the project enhances rather than disrupts the local ecosystem. The rockfill embankment beneath the caissons isn't just dumped rock, it's precisely graded and placed using underwater bulldozers and specialized placement vessels. Each rock is selected for specific size and characteristics, creating a foundation that will remain stable for centuries. The project also employs cutting-edge underwater concrete placement techniques, using trimming methods that ensure high-quality concrete even in the challenging marine environment. This attention to detail ensures that the infrastructure will withstand the test of time while providing a stable foundation for Monaco's future growth. This remarkable project proves that with innovative thinking and advanced technology, we can create sustainable solutions that benefit both human development and environmental preservation. Welcome to southeastern Turkey, where we're about to witness one of the most challenging bridge construction projects in recent memory. The Nibi Bridge, constructed by Turkey's renowned Gulsan Holding, represents a triumph of engineering over some of the most difficult terrain and conditions imaginable. This isn't just a bridge, it's a testament to human ingenuity and determination. The Nibi Bridge spans a dramatic valley in the Mardin province, connecting communities that were previously separated by challenging terrain. This region presents unique engineering challenges. Extreme temperature variations, seismic activity, and complex geological conditions that would make even experienced engineers pause and reconsider their approach. The bridge design had to account for temperature swings from scorching summer heat exceeding 40 degrees Celsius to winter conditions well below freezing. Additionally, the region's seismic activity required innovative earthquake-resistant design solutions that go far beyond standard bridge construction practices. The foundation work for the Nibi Bridge represents some of the most sophisticated geotechnical engineering you'll find anywhere in the world. Gulsan's engineers conducted extensive soil investigations using advanced drilling techniques, including continuous flight auger drilling and rotary core drilling that penetrated more than 80 meters below ground level. The foundation system employs large diameter drilled shafts, some exceeding 2.5 meters in diameter and extending to depths of over 60 meters. These aren't simple concrete pillars. They're complex engineered structures with specialized reinforcement cages that were fabricated off-site and transported using heavy-duty cranes capable of lifting over 200 tons. The pile installation process utilized state-of-the-art drilling equipment, including rotary drilling rigs with Kelly bars extending up to 70 meters in length. These machines use advanced hydraulic systems that can generate drilling torques exceeding 500 kN while maintaining precise vertical alignment even in challenging geological conditions. The concrete placement for these deep foundations requires specialized techniques. Gulsan employed trimmy concrete placement methods, using high-performance concrete mixes specifically designed for deep foundation applications. The concrete includes specialized additives that prevent segregation during the long placement process and ensure uniform strength throughout the entire depth of each pile. The bridge superstructure showcases cutting-edge pre-stressed concrete technology. The main girders were constructed using the balanced cantilever method, a technique that requires incredible precision and advanced temporary works. This method involves constructing the bridge deck in segments, working outward from each pier simultaneously to maintain structural balance. The construction process employs formed travelers, sophisticated mobile construction platforms that move along the bridge as each segment is built. These aren't simple scaffolding systems. They're precisely engineered machines weighing over 400 tons each, equipped with hydraulic jacking systems that can adjust their position with millimeter accuracy. The pre-stressing system represents the pinnacle of modern bridge construction technology. Gulsan utilized post-tensioning cables with ultimate strengths exceeding 1,860 megapascals, anchored using specially designed anchorage systems that distribute loads across the concrete structure. The tensioning process is computer-controlled, with each cable tensioned to precise loads while monitoring elongation and load transfer. The pre-stressing cables aren't just straight tendons. They follow carefully calculated parabolic profiles that optimize the structural efficiency of the bridge. This requires precise placement of ducts during concrete placement, followed by cable installation and tensioning that must be completed in a specific sequence to maintain structural integrity throughout the construction process. Given the seismic activity in the region, the Nibi Bridge incorporates advanced earthquake protection systems. The design includes seismic isolation bearings at the pier supports, sophisticated devices that allow the bridge deck to move independently during seismic events while maintaining structural integrity. These bearings aren't simple rubber pads. They're complex engineered systems combining high-damping rubber compounds with lead cores that provide both flexibility and energy dissipation. Each bearing is manufactured to precise specifications and tested extensively before installation to ensure optimal performance during seismic events. Throughout the construction process, Gulsan implemented comprehensive quality control measures that exceed international standards. Every batch of concrete is tested not just for compressive strength, but also for durability characteristics, including chloride permeability, freeze-thaw resistance, and alkali-silica reaction potential. The pre-stressing operations include load testing of sample cables, verification of concrete strength before tensioning, and continuous monitoring of cable forces throughout the construction process. Advanced instrumentation systems monitor structural response during construction, providing real-time feedback that ensures the bridge performs exactly as designed. The construction required specialized equipment not commonly seen on typical bridge projects. Heavy-duty crawler cranes with lifting capacities exceeding 600 tons position precast segments and major structural elements. These cranes were equipped with advanced load monitoring systems and precise positioning controls that ensure safe and accurate placement of critical components. The concrete placement operations utilize sophisticated pumping systems capable of delivering concrete to heights exceeding 100 meters while maintaining workability and quality. These systems include specialized pumps with pressure capabilities exceeding 200 bars, combined with distribution systems that ensure uniform concrete placement even in challenging geometric configurations. Despite the challenging construction environment, Gulsan incorporated numerous sustainable construction practices. The concrete mixes include supplementary cementitious materials such as fly ash and silica fume, which not only improve durability but also reduce the environmental impact of cement production. The construction process implemented advanced dust control measures and noise reduction techniques to minimize impact on local communities. Water management systems ensure that construction activities don't adversely affect local water resources, while waste reduction programs minimize the environmental footprint of the construction process. The completed Nibi Bridge stands as a monument to modern engineering excellence. The structure incorporates monitoring systems that continuously assess structural performance, providing valuable data for future bridge designs in similar challenging environments. The bridge's design life exceeds 100 years, ensuring that this vital transportation link will serve the community for generations to come. This remarkable project demonstrates how advanced engineering techniques, innovative construction methods, and dedicated craftsmanship can overcome even the most challenging construction conditions to create infrastructure that truly improves people's lives. From bridge construction, we now shift our focus to one of Europe's most impressive marine construction projects. At the port of Punta Langostera in Spain, we're witnessing the manufacture of 22 massive concrete caissons destined for the port of Aberdeen in Scotland. This project showcases the incredible scale and precision required for modern port construction. The Aberdeen Harbour expansion represents one of the most significant port development projects in the North Sea region. These 22 caissons aren't just large, they're absolutely massive structures, each weighing over 15,000 tons and standing more than 35 meters tall. To put this in perspective, each caisson is taller than a 10-story building and weighs more than 100 fully loaded commercial aircraft. The port of Punta Langostera was specifically chosen for this project due to its world-class caisson manufacturing facilities. The port features specialized dry docks with precise dimensional control, advanced concrete batching plants capable of producing high-performance marine concrete, and heavy-duty cranes with lifting capacities exceeding 1,000 tons. The manufacturing facility operates like a highly sophisticated factory, with each caisson moving through carefully planned production stages. The dry dock areas are equipped with precision leveling systems that ensure each caisson is constructed to tolerances measured in millimeters, not centimeters. These caissons require concrete that can withstand decades of exposure to the harsh North Sea environment. The concrete mix designs incorporate specialized additives including silica fume, fly ash, and corrosion inhibitors that protect the embedded reinforcement steel. The concrete achieves compressive strengths exceeding 50 megapascals while maintaining workability during the extended placement operations. The batching plants use computerized mixing systems that monitor and adjust mix proportions in real time, ensuring consistent quality across the massive volumes of concrete required. Each caisson requires approximately 3,000 cubic meters of concrete, enough to build several large commercial buildings. The reinforcement systems in these caissons are incredibly complex, with steel tonnages exceeding 800 tons per caisson. The reinforcement isn't just randomly placed. It follows precise engineering drawings with bar spacing tolerances measured in millimeters. Specialized bar bending equipment creates complex shapes that optimize structural performance while accommodating the various openings and features required for port operations. Advanced welding techniques join the reinforcement assemblies, with every weld inspected using ultrasonic testing methods. The reinforcement layout includes sophisticated detailing around openings for mechanical equipment, drainage systems, and structural connections that will be made after installation. This remarkable project demonstrates the global nature of modern construction, where specialized facilities in one country can efficiently manufacture components for projects hundreds of miles away, showcasing the incredible capabilities of contemporary marine engineering. For our final segment, we're exploring one of the most fundamental yet sophisticated techniques in marine construction, the installation of circular gravity cofferdams. These massive structures represent the unsung heroes of underwater construction, providing the essential dry working environment that makes complex marine projects possible. Gravity cofferdams are essentially massive steel cylinders that create temporary dry working areas in water environments. The 20-meter diameter structures we're examining today are engineering marvels in their own right. Each one is large enough to contain a basketball court and must withstand enormous water pressures while providing a safe, dry workspace for construction crews. The gravity designation refers to their method of water exclusion. These structures rely on their own weight and sophisticated sealing systems rather than complex pumping arrangements. This makes them incredibly reliable and efficient for long-term construction operations. The construction of these massive cofferdams begins with precision steel fabrication, using advanced cutting and welding techniques. The steel plates, often exceeding 25 millimeters in thickness, are cut using computer-controlled plasma cutting systems that ensure perfect dimensional accuracy. The welding operations require certified marine welders using specialized techniques for thick-section steel. Every weld undergoes rigorous inspection using magnetic particle testing and ultrasonic examination to ensure structural integrity under the extreme loads these structures will experience. Installing 20-meter diameter cofferdams requires some of the most powerful marine construction equipment available. Heavy-duty floating cranes with lifting capacities exceeding 2,000 tons carefully position each section. These cranes are equipped with sophisticated load monitoring systems and precise positioning controls that ensure safe and accurate placement. The installation process often requires vibratory pile-driving equipment to ensure proper sealing with the seabed. These machines generate controlled vibrations that help the cofferdam penetrate into the seabed material, creating an effective water seal while minimizing disturbance to surrounding structures. The bottom sealing of gravity cofferdams represents one of the most critical aspects of their construction. Advanced Tremie concrete placement techniques create an underwater seal that prevents water infiltration. This concrete must be specially formulated to maintain workability during underwater placement while achieving the strength and durability required for long-term performance. The dewatering process utilizes high-capacity pumping systems that can remove thousands of gallons per minute while maintaining precise control over water levels. Advanced monitoring systems ensure that pumping operations don't compromise the structural integrity of the cofferdam or surrounding structures. These remarkable structures demonstrate how fundamental engineering principles, combined with modern technology and materials, continue to enable increasingly complex and ambitious marine construction projects around the world.